Hi, my name's Will Krozik, Scientific Services Manager at Chemical Computing Group. Today I'd like to demonstrate the fragment-based drug design tools that we have in Mo. During this session we're going to look at scaffold replacement, or more specifically the select R atoms operation, which is what we can use when we'd like to explore multiple attachment points. We'll then be minimizing and scoring each of our newly generated ligands within the receptor environment as if we'd docked them. So let's get started. So I'm going to use the Open button to retrieve the file that we're going to be working on today. I'll just go ahead, select that, and click OK, and I'm greeted with this Load PDB file panel, which allows me to select what data we want to load into Mo. Here I'll accept the defaults, and we see the structure of human P38 MAP kinase appear in the main Mo window. Notice that it's coloured by secondary structure, with beta sheets in yellow, helices in red, and turns shown in blue. Now, before we can start thinking about fragment-based drug design, the first thing we need to do is prepare this model. Given that it's a raw PDB file, it typically doesn't have any hydrogens or charges included. There might even be some missing loops. So for that reason, I'll navigate to QuickPrep, our automated preparation wizard, the panel comprising three main sections. The first handles preparation and cleanup of the structure. Second sets tethers and restraints. The third handles refinement. Again, I'm accepting the defaults, so I'll just click OK to initiate the calculation, and I get a message at the top left of the main Mo window to give me a progress update. Before I move on, I just want to quickly explain what's going on in the background, so I'll reopen the QuickPrep panel. The first preparation stage ensures that we've got a complete model. What we're doing here is adding in missing hydrogens, charges and side chains, and also building any missing loops up to 10 residues in length. Protonate 3D optimizes the ionization states of the bound molecules and their side chains. It also generates a hydrogen bonding network through the placement of polar hydrogens. By default, we tether the atoms within the active site, and we do that to ensure that we can retain the original geometries of those atoms as captured by crystallography. We don't want to lose those geometries to processes such as energy minimization. Likewise, we can fix any atoms that fall outside of the active site, and we can do that for reasons of computational efficiency. The final part of QuickPrep is the refinement stage, which performs an energy minimization to ensure that we don't have any clashes in the structure. So I can see the message has gone from the top left of the main Mo window, and for that reason I'll cancel the panel. And next what I'd like to do is have a better look at the co-crystallized ligand and its interaction in the binding pocket. For that I'll hit Site View. Site View will isolate the ligand together with any residue within 4.5 angstroms. And next what I'd like to do is render our system. So for that, I'll use the System Manager and pin that to the main Mo window as a means to manage all of the data that we have in the system. From here, I can hide and show different atom sets, I can make selections, I can generate surfaces, but today I'd like to use it to adjust our rendering. So I'll start by hiding the ribbon, and next what I'd like to do is color our ligand a bright color to allow that to stand out. So there we have our prepared model rendered as we'd like. So next what I'll do is click on the Compute pull down to access the tools that we have under the umbrella of fragment-based drug design. So here we have these different operations that can be performed. They all point to the same unified panel, but I'm going to start with scaffold replacement. The panel comprises four main sections, the first allowing us to define the system in terms of the ligand and our receptor. The second allows for defining the type of operation we'd like to perform, and you'll notice these options are the same as what we saw earlier within the Compute pull-down. The third allows for filtering, be it by descriptor filters or pharmacophores. And the final part allows for refinement and scoring. In a previous example, we selected specific atoms to replace on our scaffold with defined attachment points. So that was using the scaffold replacement operation that I'm currently showing now. Here we have the atoms to be replaced. We see those in the green halo. We see that we've got two defined attachment points. However, sometimes we might not know our attachment points, or perhaps we just want to explore different attachment points. In those circumstances, what we can do is change our operation from the select scaffold operation to the select R atoms. And as before, the panel guides us to set up our run. It's saying to select the first heavy atom of each R group. So I'm going to select this as the starting point for our scaffold replacement operation. And because I don't know where I want the endpoint to be, I'm going to select 3 different atoms. So effectively, this is going to run 3 scaffold replacement queries, but simultaneously. In this case, we see that we've got 3 different attachment points at the end here, representing those different points that we selected here. And if I go back to the panel, now that we've selected the operation and our heavy atoms to replace, I can move on to look at the next part of the panel, which handles the filtering. So here I can see that we've got some default filters applied in terms of a molecular weight cutoff, a TPSA range, and a note on reactivity. I also notice that the Check Filters button is coloured red, and if I just hover my mouse to raise bubble help, it tells me this button is coloured red if the ligands do not pass the descriptive filter. To get more information on that, I can click on the button. I get a readout at the top left of the main Mo window, which tells me the molecular weight of the co-crystal ligand is 528, and I can see that's not going to pass the descriptive filters. So we need to change it, and I can just use my keyboard to type in and push that cutoff up to 600. And with that, I'll move on to the final part of this panel, where we can think about refinement and scoring. So today I'm going to opt to minimize the generated structures within the receptor environment, and I'd also like to write a score to the output database as if we docked these ligands. So if I click on the score pull down, you can see that we've got these different scoring options. I'm going to select GBVI-WSA, which is our tried and published method. With that, I'll go ahead and click search to initiate the calculation. Mo is now searching for scaffolds to replace the atoms that we see in the halo between the bond vectors, whilst preserving the geometry of the fragments that fall outside of these attachment points. This time though, we're effectively running 3 queries, the first replacing the scaffold between this point here and this point here. The second run will do it from here to here, and the third will do it from here to here. So effectively 3 queries in one. We could be running 3 separate scaffold replacement queries, but this is a much easier way to do it using the scaffold replace R atoms. In the background, Mo is searching a fragment linker database containing just over 40,000 structures, but we do have options to larger ones if they are needed. The results themselves are written to a database viewer, which is our format for displaying database entries, or in this case, database results. It looks and feels much like an Excel spreadsheet, but if I just drag the mol field open, you can see this actually contains the 3D structure of our newly generated ligands. It's also our launching point to various tools that we have in Mo. So for example, here we could jump into QSAT. In this case though, I'm going to use the database viewer to peruse some of the quantitative data that we have here, such as the RMSD field, which tells me the RMSD of the newly generated ligand relative to the co-crystal. And we can also have a look at GBVI-WSA, the scoring function that we requested to be written to that output database as if we had docked those structures. Now we've already generated close to 100 structures, so I'm just going to stop that search prematurely. And what I'll do next is what we can do is just sort our database according to the scores. So we can sort by any of these fields by right-clicking, click sort, and I'll sort ascending. It'll ask you, sure you want to reorganize the database? Yes, I am. And now we see that the best scores are written at the top of the database. So this score is an energy. The more negative that value becomes, the better. I can also have a look at these in the 3D environment. So if I just go ahead and open up a database browser, that will display the ligand in its 2D schematic as well alongside the 3D version in the receptor environment. If I just minimize that 2D view and deselect the atoms, we can see the newly generated ligand shown in green against our original co-crystal ligand shown in orange. Within the browser, I can add different fields. So for example, if I'd like to see the RMSD of each entry, along with perhaps the score, we can see that they're written here, as well as at the top left of the main window. And I can just cycle through now to have a look at some of those newly generated structures. As we go through, we'll see that they have different lengths according to the different attachment points that we specified. So that brings us to the end of today's session, where we use the scaffold replacement operation to generate novel scaffolds where we don't have specific attachment points. We customized the descriptor filters to be able to provide us appropriate structures, and then we also minimized and scored within the receptor environment. I hope you've learned a lot today. If you have any questions, please do reach out to me at support@chemcomp.com.